So let me do a very, very simple, running example. It's a straightforward matrix multiplication example that really just illustrates the basic features of memory and thread management and so on. We're not going to be talking about shared memory in this version, and it's essentially we'll be looking at local register usage. We're talking about thread ID usage. And we'll talk about memory data transfer APIs between hosts and devices. So what we're going to do is we're going to be looking at square matrix multiplication. And there's an n matrix multiplied by n matrix. And each one has a width. So this width can be essentially as a constant that you can instantiate into a number. And we're going to be talking about matrix multiplication without tiling. Okay? Ultimately, you're going to have to do tiling on this architecture in order to get general executable code. But this code will work for limited cases. Okay? But it's just essentially there for you to understand some of the basic concepts. And so what we're going to do is we're going to have each thread calculate one element of the result array. Okay, remember we have width by width, right? So for a, let's say, 64 by 64, we'll have 2 to the 12th, which is 4K elements. So we'll be generating 4K threads, okay, for this computation. Each thread is going to take one row of n and one column of n to the dot product, right, and generate this. Easy enough? Right? Very straightforward stuff. One thing you should notice is that in order for us to use independent threads, each one doing this kind of operation, all the elements of n will be read multiple times because one thread is going to read the first row and the first column of n, but the next thread will also read the first row of n and multiply by the second column of n. So each element of n is going to be read with times. And each column of n is also going to be read with times. So for a 64 by 64 array, each element is going to be read 64 times. This is not a very memory bandwidth efficient way of doing things, okay? And we're going to talk about how you address this problem later with tiling, right? But now, we're going to be inefficient for the moment. So we're going to start with data transfers, okay? So we can allocate, some device memory where we'll copy. Let's assume that, in the main program, in this user, in the main host code, you're going to have a n array, right? And you're going to do some I/O to lead in that array or something, right? There's something that will lead into this thing that I'm not going to really worry too much about. But then you're going to have an NP version that is going to be, on the on the GPU, and then you're going to actually, allocate. This is just a little structure. It doesn't really have all the elements, right? It's just that little structure, that matrix type. Remember that matrix type? So you're going to initialize it by width will be the block size, height will be the block size. It's not a subarray of anything else, so the pitch is also its block size. And then you can calculate the size by block size times the size of floating point. We already went through all this, so it should be very easy by now. And then you do a CUDA malloc. This is where you actually get all the elements allocated, right, in the global memory, device global memory. So that requires the ND, the address of the pointer to the ND, and elements, and then you need to give it a size. So after this point, you have allocated all the memory you need for matrix n on the GPU, okay? And you will have a similar piece of code for n, right? So the two input matrices. Then you will do the CUDA memory copy by moving the n element contents to np element contents. You copy so many elements, and you're saying that you're copying from host to device. Okay? So after this point, the n matrix is going to be in the GPU memory. Right? Now, you can, in the end, you can also read n back from the device. So you will copy from np. You know, actually, no, you'll be copying from, let's see, read from the device. So this is actually the, this is the NP element, and you can copy it back to the CPU, let's say P, which is product, and then you can do size, you can do CUDA, and eventually you're going to change this to PD, because this is going to be the product array that we're going to be calculating. So be careful when you use the code. And eventually, after you are done with everything, you should free up the MD elements so that you don't occupy the storage on the device or on the GPU. Here is a very simple piece of code for the host. Okay, so if I were going to write that simple matrix multiplication on my CPU in ordinary C, this would be a very simple piece of code that I will write. So this is for execution on the host. Matrix multiplication on host. I'll take one input array, another input matrix. I'll produce a product matrix, right? So I'll have a 3-level. Remember that 3-level loop? The first 2 levels generate the 2 dimensions of the product, and each one will be a dot product, right? One row of the input and one column of the input. I will use the inner loop to do the dot product. So this will be a very simple CPU code. And in the inner loop iteration, what I will do is I will use k, which is the innermost loop iteration variable, to go through the row. So this is a row traversal, and this is a column traversal. Remember, in C, all the layout of the data structure is in row major. That is, all the row elements are in consecutive locations, and then you have another row, you have another row. In order for you to access the column, you need to jump, right, in the real memory. And that's why you have k times n width plus j, and this is how you actually jump in the column access, right? So that's a piece of C code that you will write to do matrix multiplication. So what we do is we will just multiply using one thread block for this example. Okay, we're not going to generate any more than one block for this example. And the block is going to be organized into 2 dimensions. Okay, and each dimension corresponds to one element. Right? So I would take essentially for a 4x4 matrix multiplication, I will generate a 4x4 block, and each thread will calculate one result element. Okay? So when I call the kernel, I will say grid only 1. Okay? Only 1. And then for block, I will have 4 and 4 in that dim structure, and then 0 in the third dimension. Right? And then I would call the kernel. And the kernel code, the kernel code is going to be the code that you need only for one of the elements. So the kernel code will not have the outer 2 levels of the loop. It only needs to do the dot matrix, because the outer 2 levels are implicitly expressed by the dimensions of the thread block. Okay? By generating so many threads, you already took care of those iterations. Okay? Now, each thread will load a row of matrix M, it loads a column of matrix N, perform multiply, and then eventually accumulate into something, and then eventually write the product into the object memory. Do I want to go into that? Sure. So the size of the matrix is limited to the number of threads allowed in the thread block. And you can only have up to 512 threads in a block. So the size of the input matrix with square cannot exceed 512. So for a square matrix multiplication, you won't be able to do more than a, what? 256, right? That's 2 to the 8th, right? That's 16 by 16. That's the biggest array you can do with this particular way. Because in CUDA, you can only have up to 512 threads in a block. That's a limitation. The matrix multiplication, when we want to execute the matrix multiplication on the device side, we're going to have we need to start with a piece of main program code. So essentially, we will do the usual things. We'll have the N and P, that we will have in other matrix multiplications. And then, eventually what we want to do is we want to be able to do matrix multiplication on device, okay? That, I can actually have, these things, done in the device. But we need to transfer data. We cannot just do this directly. And eventually we want to return free the storage. So what we do is we will allocate ND and ND on the device. And then we will copy from N to ND. So this should be fairly straightforward to you at this point, right? And then I will do, I will also allocate a product or matrix on the device to hold the results, right? So I'll allocate a P on the compute device. And eventually I will copy from the product on the device back to the CPU product. And that gives me the answer on the CPU. Okay? In order for me to do this, you need to fill in a little bit more details. You need to declare, remember these are the configuration variables that I'm going to initialize. So, I'm going to actually have the matrix size and matrix size in the 2 dimensions. Whenever you don't put in the 3rd dimension, it's automatically 0. And then for the grid, I only have 1 grid. Okay, 1 block in the grid. So it's 1, 1. Okay, I don't generate any more than 1 block in the grid. So I will initialize this, and I will call the kernel after all those transfers. And when I invoke the kernel will translate into matrix size by matrix size threads. And that will do the computation, and eventually you will copy the code from device back to the CPU. Okay? So now we're going into this kernel code. So then you will actually go to the M elements. This is the M array. You will take the TY index because you need to skip over so many things in order to get to this row, right? So you take TY and multiply TY by the pitch. And in this case, the pitch is initialized to just the width because it's not a subarray of anything else. Imagine if there's if this is just a subarray of a bigger array, then you need to use the pitch, the real pitch. So this term skips you over to the beginning of the row, and then you will iterate over k so that you will walk through k, through the row, right? And this thing does the column side. Essentially, you will say, I'm going to take n pitch. So this, I'm going to skip, in order to get to one of these elements, I'm going to have to remember the k that I'm at and multiply k with the pitch so that I can skip over to the beginning of the row here. And then I would use tx to actually go to the element. So this thing allows you to walk over the column. These two will be loaded into the m and n elements, and you do the multiplication, you do the accumulation, iterate, and you generate the final dot product. Okay? So this piece of code will have 256 instances, all running at the same time. Okay? Each one will just use the its own TX and TY to generate, to access the right portion of the memory, and does the work. And this is what we mean by data parallelism at the end. Am I recording? Yes, good. So what we're saying is the generation of all these elements of a big data structure can run in parallel. And each one will be accessing a different part, or in some cases the same part of the memory, right? And they are all using data parallelism to do the work. So far, so good. There's some loose ends that I have not, cleaned up yet. First of all, I kind of use what's called the allocate device matrix, and it's just a convenient function that you can use in order to make the allocation a little bit cleaner. So, because you have a data structure matrix M gives you the dimensions and also the element pointer, right? So instead of using a CUDA malloc, and you need to give these sizes, you just say allocate a matrix, and you write a user function where you actually initialize the M device and the width and so on, so that you actually call that CUDA matrix. It just makes your code look a little better. So this is standard software pipeline, software engineering kind of thing. And then you can free the matrix, and then essentially what you really do is you go and free the pointer to the elements, the storage of the elements. And that's pretty much the memory allocation. You can essentially make your code look a little bit more pleasant by wrapping the system memory allocation routine with your own cleaner memory allocation routine. And then you can do copy to device matrix and copy from device matrix. These will be your own user code. Again, because you have all these data types that gives you the size and all that you can write a cleaner looking function call, but within that you actually do some data manipulation so that you eventually call the real memory copy with all the options and so on, that it becomes, you give the details within the function. So this is how you can make your CUDA code looks a little bit basically. This slide is designed to give you the idea of how you can handle arbitrary size arrays. Remember, the blocks can have only up to 512 threads. Okay, so if you have a input matrix of, let's say, 1K by 1K rather than 16 by 16, then you're out of luck with the code that we have so far, right? So in order to make the code capable of handling much bigger input matrices, you can have essentially 2D thread blocks to compute, let's say 16 by 16. So this is a block width constant, and you can have 16 by 16, 8 by 8, 4 by 4. It's up to you. Okay, and so once you decided that factor, then you create a 2D grid. And you take the real width of the array, the matrix, and divide it by the block size, you get the number of blocks that you would need. So you will essentially create all these square block blocks, and each square block will correspond to a thread block, and you will generate all these thread blocks to calculate different parts of a bigger array, right? But whenever you do so, you also need to be careful, because in your kernel code, it's no longer just TX and TY. Now you also have to figure out your block ID, right? When you calculate the part of the memory that you're going to be accessing. So the addressing will now need to factor in the block ID and the thread ID. Okay? And even with this, you can still run out of luck when your input matrix is more than 2 to the 16 elements. Okay, because you can only use 2 to the 16, right?
65,000.
I think it's 2 to the 16 blocks in each dimension.
In each
that you're
dimension,
allowed.
yeah. And then plus whatever the multiplied by the block size.
So it's something like a million elements.
2 to the 4. So yeah, about 2 to the 20th.
Yeah.
Right, for each dimension. Once your matrix goes beyond that level, you will need to have a loop that wrap around the kernel to actually iterate through these things.
And more memory.
And more memory. Okay. So, this is just meant to give you a flavor of, how you can make your code more and more general and more capable of handling these arbitrary size and so on, right? So once we're done with this, you have a piece of code that can generate, in the first version, up to 512, 256 in the square case, threads. So that's an accomplishment. Okay, you can, suddenly you know how to handle threads, you know how to transfer data, and so on. And that's essentially what David Kirk and I have been talking about. With the CUDA programming model, we can actually teach you how to do parallel programming in 1.5 hours. Okay, and that's really what I did, right? I spent an hour and 20 minutes yesterday and 10 minutes today to just teach you how to do parallel programming. If you go and implement this piece of code, and with everything said and done, you run this piece of code, you're going to get, you need to get to this level to handle bigger matrix. Okay, 16 by 16 matrix is not going to give you enough computing requirement to get a lot of speed of this hardware. So typically, you will get something like 1K by 1K matrix before you see some real performance benefit of this kind of hardware. So you'll be totally excited. You go and run it, and let's say you have a 4K by 4K matrix that your advisor always wanted you to handle. Okay, and then you run it and say, oh, it's going to be 356 gigaflops, and I'm going to be home free. Before you go and talk to your advisor, make sure you check the numbers, because you're going to get probably right around 10 gigaflops. Okay, it's going to be 3% of the 356 gigaflops that you were hoping to get. Okay, and so the rest of the class is to teach you how to get much closer to 356. In fact, the best code that people have done so far is 93 gigaflops. So you have about 9 times to go from here to the end of the class. Okay? And that's where parallel programming really gets hard. Okay? And there are going to be harder things, there are going to be less hard things. And we're going to take you through that.